Elasticity. So now elasticity is a property of any material. In this material, if we apply any external force to this material, then the material will stretch. Any substance, let's for example take a rod. So I have one steel rod, and on this rod I have applied an external force. Now this external force is my weight. This is my weight, and this weight is applying a downward force on it. So now due to this force, the material will change. The dimensions of the material will change. What do you mean by dimensions of the material? The size, shape, length, volume, all these properties of a material will change when some external force is applied to it. This external force can be of any form. So this is my material and it has changed. Now where this elasticity comes to the point, it's when after removal of this force, now first I have put a force, the dimensions have changed, the rod has become longer. After removal of this force, once I have removed this force, this rod will go back to its original shape and size. That is, this rod will go back to its original dimensions. This is known as elasticity. What the first thing we learned was any substance, any material, if we apply any external force, the material will stretch, the dimensions will change. That is normal, that is natural. But after I have removed the weight, or after I have removed the force completely, this material has to go back to its original shape and size, to its original dimensions. This is known as elasticity. This is known as the property of elasticity. Okay, now let us take an example. This is butter. Butter will not show elasticity. Why? Because this is my slab of butter. I will melt this butter and I'll put it in a vessel which is cylindrical in shape. This vessel is cylindrical in shape. You can see from its base it is circular. So after I have melted the butter, which was first a rectangular slab, and then I have kept it into a vessel, and then I remove it out, this will become a cylindrical. So butter, which was rectangular slab, it was a cube, have now become a cylinder. After removing of this force, this butter will not go back to its original shape and size. It will remain a cylinder until we again put it into some other mold which is cubical and then convert it into a slab. We'll first define elasticity. Elasticity definition: the property by virtue of which material bodies regain their original dimensions, that is size, shape or both, after removal of deforming forces is called as elasticity. It's the same thing. I first have a steel rod. This is my original size, the original length of the steel rod, let's say L. To this I have applied an external force, I have applied a weight. Now this weight will pull the steel rod downward. This is my second phase. Due to this weight, my steel rod is being pulled downward. This was its original length L. This is L plus some other length L. This is my increase in length. Let's name it a small l. Now, in the third step, what happens is I remove the external deforming force. I remove the external force which was leading to increase in the length of the rod. After removing the force, it will go back to its normal length L again. So, if you see the length of step number 1, this is 1, 2, 3, 4. This length, that is the dimensions of step number 1 and step number 4 are the same. In step number 2, what happens is due to this force, there is deformation taking place, and in step number 3, this deforming force is removed, therefore it goes back to its original dimensions. And from this, the definition of elasticity, and from this diagram, what did we learn? Is after deforming force is removed. What was the deforming force in the diagram? It was this force. It was this weight W which was leading to change in length, which was leading to increase of the length. So after this deforming force is removed, it is removed. In the third step you saw, in the third step the deforming force was removed. After the deforming force is removed, what happens is the substance regains its original dimensions. The original dimensions, what was the original dimension? The capital L. Okay, over here the original dimension was L. In step 2 it was L plus small l. It was L plus small l. Over here it was again L plus small l, and over here it was capital L. So in step number 1 and step number 4 both the dimensions were L, but in 2 and 3 it was L plus small l. So after this the deforming force is removed, the original dimensions are regained. But some materials undergo permanent deformation, that is, do not regain original dimensions. This is the example of butter which I showed you. That butter is there, you melt it, you put it into a circular vessel, it becomes circular, but after you remove it from a circular vessel, it won't again turn into a cubical block. So what happened in butter was it did not show any form of elasticity. Why? Because it does not possess the virtue, it does not possess the property of elasticity. That is, once the cube is given into the vessel, it turns into a circular cylinder. It cannot go back into its original form, that original cube form, until we put it into another mold which is cubical. So, but some materials undergo permanent deformation. This has permanently turned into a cylinder. That is, do not regain original dimensions. Such materials do not possess the property of elasticity. Butter does not possess the property of elasticity. So now the question is, if they do not possess elasticity, then what property do they possess? The other property that materials like butter have is plasticity. Now what is plasticity? Plasticity is once any material or any body which does not possess elasticity, that is a plastic material, will go under deformation, and after going under deformation it will never regain its original shape or size. Let's see the definition. The property of a material to undergo a permanent deformation even after removal of external deforming forces is called as plasticity. For example, clay. If you have ever played with clay, if you make a flower out of a clay, it will remain a flower until a deforming force is acted upon it. Butter. If you have butter in your cubical form and if you spread it on your bread, it will become a thin layer on your bread and it won't again turn into a cubical form. Putty. Putty is the material which is used during the construction. So now I have any plastic body, any one of these, let's say any plastic body, and I have applied a deforming force to change its shape into another shape. So this was my shape 1 and this is my shape 2. I got my shape 2 how? By applying a deforming force. Now this new shape of a plastic body, it is retained by it means it will permanently be over there until I don't change it by my own self. Deformation. Now what do you mean by deformation? Deformation means change. Change in what? Change in dimensions. Deformation is change in dimensions. Now what do you mean by dimensions? Dimension is anything. Shape, size, length, volume. All these come under my dimensions. So deformation is change in any of these, or maybe one of these or two or more of these. Deformation basically means change in dimensions. Now the force which is responsible for deformation is known as the deforming force. Now I taught you this for the rod. This is my rod and this is my block. So now this block is my deforming force. The force which is responsible for deformation is known as the deforming force. Two important terms which we will be using in the entire chapter of elasticity are, the first one is stress and the second one is strain. Let's see the definition of stress. Stress is defined as the internal restoring force per unit area, cross-sectional area of a body. The internal restoring force per unit cross-sectional area of a body. What do you mean by that? Now I have this rod and I have a force that is pulling it downwards. This is the external force which is applied to it, that is pulling it downward. Now what will this body do? This body is an elastic body. So what will this body do? This body will try stopping this external force to pull the rod downwards. Therefore it will have its internal force. Let me zoom in this part of the rod for you. So this is my rod, this is the end of my rod, and this is my external force. Now what this rod will do, since it is elastic by nature, it has the virtue of elasticity, the property of elasticity, it will send its forces which are moving in the upward direction. This external force will do its work of pulling the rod in the downward direction, and this rod itself will try pulling itself back in the upward direction. This force which is applied by the rod is known as the internal force. This internal force is known as stress. Again, we'll go through the definition once again. After the explanation, you will understand it better. Stress is defined as the internal restoring force. The force which is restoring it, which is helping the rod to not change its dimension. So restoring force per unit cross sectional area. This is my area. This entire is my area per unit cross sectional area of body. The second important term is my strain. Strain is a very important term. The definition of strain is defined as change in dimensions per unit original dimensions. That is, this is my original dimension. This is my length L. This is my original dimension. But over here there is change in the dimension. That is, this was my original dimension L, plus I have this increased in the dimensions, that is small l. So my new dimension is L plus small l. This is my strain. This is my new dimension. So what will my strain be? Strain is defined as change in the dimension. What is the change? How much has it changed? L, small l. So it has changed by small l. Per means upon. Per unit original dimension. What is my original dimension? L, capital L. Here length has changed as compared to the original length. Now we'll see the formula of stress. Formula is applied force upon area. Applied force means the internal force that we were talking about over here. This is my applied force. So this is my elastic restoring force upon area. The dimensions over here are L minus 1, M1, T minus 2. And for my strain, when we talk about the strain, it is change in the dimensions upon the original dimensions. Over here my strain is dimensionless quantity. Now why is strain a dimensionless quantity? Because if my original dimensions was length, that is capital L, and my change in dimension is small l. Okay, now let's take this example of volume. So this will be change in volume. Let's think that it is dV upon the original volume, that is capital V. So this will be length upon length. Let's assume that the length is in centimeter. Then even over here the length will be in centimeter. If we assume that the volume is centimeter cube, then even over here my volume will be centimeter cube. So this will cancel out this. This will cancel out this. So if my numerator and denominator are cancelling out each other, then there will be no dimensions left, and hence it is a dimensionless quantity. So when I say my strain is a dimensionless quantity, you first have to think that why it is a dimensionless quantity, because the same units are being divided and then they will cancel out each other. Types of stress. So there are three different types of stress and three different types of strain. We'll go with the first one, that is longitudinal or tensile stress. When we talk about the longitudinal stress or the longitudinal strain, we will be talking about the length, the change in the length, and everything which is related to length, that is longitudinal. Formula given is applied force upon area of cross section. So now over here let's say that I have a weight which is applying some force F. So here we have in the formula F by A, that is upon area of cross section. This is the area of cross section. So if we see this area of cross section, it is basically a circle. The area of a circle, the circular area will be pi r square. So this is F by pi r square. And over here, the weight is doing the work of a mass in the direction of gravity. That's why it will be mg. So instead of F, we have mg. Instead of A, we have pi r square. Thus, my final formula will be mg by pi r square. So when it comes to the formula of longitudinal stress, you can either write by applied force upon area of cross section, or F by A, or F by pi r square, or mg by pi r square. All of these are valid formulas for longitudinal or tensile stress. Moving on to the longitudinal or tensile strain. What is strain? Again, when we talk longitudinal, we'll talk about the length. So the formula will be change in length upon the original length. Now what do you mean by change in length? Suppose if this is my rod, this is my original rod, and this is my change in the rod, that is my change in the length. If this is my original rod, let's say the length is L, over here also this much the length will be L, and this extra length will be small l. So the change in length will be final length minus original length. What is my final length over here? The L, capital L, which was there from before. In addition to that, plus that, we have this small l. Therefore, my final length will be L plus L. L plus L. Minus the original length. Original length is L. So, L plus L minus L. L plus small l minus capital L upon the original length, that is capital L. This will get cancelled. So, my strain will be small l by capital L. So, these are my longitudinal stress and longitudinal strain. Moving on to the second type of stress and strain, that is my volume stress and volume strain. So, if we go to the volume stress, it will be change in volume. Over here, we will be talking about the change in the dimension, and that dimension is volume. The changes, all the changes will take place in terms of volume. For that, we have considered this cubical block. To this cubical block, we apply pressure from all the four sides. We apply pressure from all the four sides, and after applying pressure from all the four sides, the cubical block decreases in size. Okay, so now over here, let's say V is my original volume. V minus dV is my final volume. This small chota change in the volume is my dV. dV is my small change in the volume, and V minus dV will be my final volume. So this V minus dV is my final volume. V, capital V, is my original volume, and dV is the decrease in the volume. So again, volume stress will be applied force upon area. What force did we apply in this? The force we applied was pressure from all the four sides. So my applied force will be pressure into area. Why? Because we are applying pressure over the entire area. Upon area, that is the original area. So this A and A will get cancelled. The formula for my volume stress will be only dP, that is change in pressure. That is my applied force. Moving on to the volume strain. Volume strain is again, the formula will be change in volume upon original volume. What is my change in volume? dV. What is my decrease in volume, that is change in volume is dV, and original volume is V, that is given to us. Therefore dV by V is the formula for volume strain. The last type of stress and strain we are talking about, the third type of stress and strain, is the shearing stress and the shearing strain. What do you mean by shearing stress? Shearing stress means change in the angle, change in the shape. Now, for this we have taken an example of a block. The orange colored block is my original block. To this I have applied some type of stress or some type of strain on the upper body. Due to this, the shape of the block will change a little and it will become a little slant. My orange original block is a straight block over which I applied some tangential force, some type of strain, due to which it became a little slant. And my red color block is my slant block. Remember, the down surface, the surface which is down will be the same because we are applying force above in the on the upper body. So over here, the original block, that is the orange colored block, and the changed block, that is the red color block, will make an angle, and that angle will be theta. So what is the formula? Tangential applied force upon area, that is force upon area. Over here we are applying force tangentially on the upper body. We have the shearing strain. Shearing strain is what? Relative displacement of any layer upon its distance from the fixed layer. Which is my fixed layer? A, B, C, D is my fixed layer. Okay, A, B, C, D and the upper body E, F, G, H is my original block. But what happened? I put a force on it. Therefore, A, B, C, D will remain A, B, C, D, but the upper body will just, the upper part will just shift a little. So from E it came to E dash, from F it came to F dash, from H it came to H dash, and from G it came to G dash. So it's upon the distance from the fixed layer. When you calculate this in the form of theta, you will get tan theta. And since my theta is very small, tan theta will be approximately equal to theta. So my shearing stress is F by A and my shearing strain is theta. Hooke's law statement: within elastic limit, stress is directly proportional to strain. That is, stress is directly proportional to strain. Now within the elastic limit is the limit within which the body will possess the property of elasticity. The body will act as if it is an elastic body. Within the elastic limit, the body will act as if it is an elastic body and it will possess the property of elasticity. So within that, stress is directly proportional to strain. How much stress is given, how much force is applied, that much change will happen. So now we have stress directly proportional to change. Whenever we want to remove a proportionality sign and put an equal to sign, we add a constant. So stress is equals to M strain. So now what will M be? Stress upon strain. This is my Hooke's law and M is my Hooke's constant. They have just showed it over here, the stress and the strain slope. For example, let's say we are at this point. If my stress is 5, my strain will also be 5. If we are at this point, if my stress is 20, my strain will also be 20. If my stress is 15, my strain is also 15. Stress is directly proportional to strain, and whatever the slope is, it is the modulus of elasticity. This M is the modulus of elasticity. This is a new term. We have 3 types of modulus of elasticities coming up, known as elastic constants. Now elastic constants, I said 3 types. They are Young's modulus, bulk modulus and modulus of rigidity. We had 3 types of stress and 3 types of strains. The 3 types of stress were longitudinal stress, longitudinal strain, volume stress, volume strain, and shear stress and shear strain. Young's modulus deals with the longitudinal stresses and the longitudinal strains. Bulk's modulus deals with the volume stresses and the volume strains, and modulus of rigidity deals with the shear stresses and the shear strains. We'll first move on to the Young's modulus, which has a symbol of capital Y, Young's modulus. It is related to change in length of the body. Let's see the definition. Young's modulus is the ratio of longitudinal stress upon longitudinal strain. Let's see the formula. We'll write the same thing which is there in the definition. Young's modulus is longitudinal stress upon longitudinal strain. Now longitudinal stress. What was longitudinal stress? What is stress? Applied force upon area. And when I say applied force upon area, so what is it? The force which is applied that is mg, we had it for the rod, upon the area pi r square. We have already found it in the previous on the previous page where I showed you the stress and the longitudinal stress and longitudinal strain. And longitudinal strain is what? Change in length upon the original length, that is L by L. We just pick up these and put it over here. That is, instead of writing longitudinal stress, I will substitute it or replace it by this. And instead of writing longitudinal strain, I will substitute or replace it by this. So mg upon pi r square upon L by L. Denominator go to the numerator. Therefore, this is mg by pi r square upon L by L. This will go to the numerator. Therefore, mgl. And this entire thing is the denominator, that is upon pi r square L. mgl upon pi r square L is my formula for Young's modulus. The dimensions of the Young's modulus are given by L minus 1, m1, t minus 2, because the SI units are Newton per meter square. Moving on to the Bulk's modulus. Bulk's modulus, the symbol for the Bulk's modulus is capital K. And again, the definition, Bulk's modulus is defined as the ratio of volume stress upon volume strain. So we'll simply write down the formula into its mathematical format. Bulk's modulus is equals to volume stress upon volume strain. Now we had found out for volume stress was dP, because dP was the only pressure that was being applied, and volume strain, that is change in volume upon original volume, that is dV by V. Instead of volume stress, we will simply write down dP. Instead of volume strain, we will simply write down dV by V. dP upon dV by V. This will become V dP by dV. The dimensions are the same, L minus 1, m1, t minus 2, because the SI units will also be same, Newton per meter square. Okay. The reciprocal of Bulk's modulus of elasticity is called as compressibility of the material. Compressibility of a material is what? 1 upon Bulk's modulus. So SI units will be completely reciprocated, that is meter square upon Newton, and the dimensions will be the opposite, L1, m minus 1, T2. Moving on to the last elastic modulus, that is modulus of rigidity given by eta. Definition, modulus of rigidity is defined as the ratio of shearing stress to shearing strain. Again, simply the mathematical formula, modulus of rigidity is shearing stress upon shearing strain. We had found out shearing stress to be F by A, and shearing stress was tan theta, which was approximately equal to theta. Therefore, we will just write down theta. So, this is F upon A theta. Therefore, this will be F by A theta. Poisson's ratio, sigma. When a force is applied to a body along any direction, there is a change in the size along the direction of the force, change in the size perpendicular to the direction of force. Now, listen to this carefully. This is a rod, and I am applying an external force in the downward direction. Due to this, what happens is the length of my rod is increasing. Change in the size along the direction of the force. Force is downward, length is going downward. Okay. Now, change in size perpendicular direction. Now, what happens? The same rod is elongated by the length, that is the length of the rod has been increased. So due to this, what happens is these force start acting towards it and it becomes thinner than what it is. Because if you want to make a rod of a particular size and shape, of a particular volume longer, it will definitely get thinner because you cannot add any material to it. So it will get thinner. So now what happens is, along with this force, there are inward forces also acting and making the rod thinner and stretching the rod. Now this force and this force are perpendicular to each other. Therefore, change in size along the direction of the force and change in size in the perpendicular direction of the force. Two forces act over here. And now this Poisson's ratio will give you the relation between both these forces. What does Poisson's ratio say? Lateral strain is directly proportional to longitudinal strain. What do you mean by lateral strain? Lateral strain means the strain in the width, in the diameter of the body, is directly proportional to the longitudinal strain. Again, what is longitudinal strain? The change in the length. Therefore, a change in the diameter, the change in the width is directly proportional to the change in the length. So, lateral strain is directly proportional to longitudinal strain. Now, this is a proportionality sign. To remove this proportionality sign, we'll put an equal to sign and we'll put a constant here. Over here, this constant is the Poisson's constant or a Poisson's ratio denoted by a sigma. Therefore, lateral strain is equals to sigma into longitudinal strain, and over here sigma will be lateral strain upon longitudinal strain. Poisson's ratio is defined as the ratio of lateral strain to longitudinal strain. Over here, with the help of this graph, I'll explain you how an elastic body works after some force is applied to it. Suppose there is an elastic body and a force is applied to it. This is my elastic body and this force is applied to it. Now with increase in force, the length of the elastic body will increase. This is my increase in the length of the elastic body. But over here, once I remove this force, it will go back to its original dimension, to the original length L. This action happens only and only when the body is within its elastic limit. Within the elastic limit, if I pull the body with the help of some force and then remove the force after some point of time, it will go back to its original shape and size. The same thing is shown over here in the form of a graph. Suppose I have an elastic body and that is increasing in length and it is at this point. Over here, if I remove the force, it will go back to its original position. But this behavior of an elastic body happens only and only till point P, because point P only and only till point E, because point E is the elastic limit. Point P is just the point before the elastic limit. It's like a warning point. Point E is the point of the elastic limit. That means that over here my stress and strain will be equal. Why? Because over here it is within the elastic limit. Now what happens is, if I cross the elastic limit of the rod, if I increase the length beyond the elastic limit and then remove my weight from the rod, what will happen is, it will again go back to its shape and size, but not the original shape and size. Maybe a shape and size a little bigger than the original one. This is my original shape and size, but on the point E dash of the graph, this will go back to a smaller shape and size, but not the original one, a little more bigger than the original one. So now what happens over here at this point, it will not go back to O. It will never go back to O. It will come back to some other point, that is S. And so this OS becomes my permanent set. OS is my permanent set. What do you mean by permanent set? This is my permanent deformation that has already happened. Now whatever you do, how much ever you try, it will never go back to the original shape and size. It will never go back to O. It will always come back to S. After Y dash also, you do not stop putting your weight or you increase your weight. That is, if you do not remove your weight or you increase your weight, what happens? It goes to a point Y dash. This point is known as the yield point, or the plastic flow begins. That is, the solid rod starts behaving like a plastic body, or starts flowing like a liquid. That is, that is, it starts increasing at a very high rate. If you see the slope, it's going upward, that is it is increasing at a very high rate. NB is the breaking stress and B is the breaking point. Now what do you mean by N? That is the breaking stress. At this point, if I have a rod which I have stressed to a great extent, and now I realize I do not want to stress it any further, and I remove my weight at this point of time. My weight is completely removed, but since it is at the point N, that is at the point of the breaking stress, it will elongate by its own self. It will elongate by its own self. Without the weight, it will elongate, and on its own it will break. So N is the breaking stress. Over here, even if you remove the weights, nothing will happen. It will eventually break. At which point? B, that is the breaking point. On my y-axis, I have tensile stress. On my x-axis, I have tensile strain. So, at point E, till point E, it will be within the elastic limit. When it will reach E dash, it will come back to some dimension, but that will not be the original dimension. It will be somewhere near the original dimension, and this is a permanent set which is being formed. At YP, this is the yield point where plastic flow begins. N is my breaking stress. Over here, even if you remove the weight, it is going to elongate further and break at point B, that is my breaking point.